Hi, welcome to the next lecture. So far we have been looking at the different components in the encoder and the decoder of the transformer, right? There are a few more elements that we need to look at which are a part of the transformer architecture. One of them is something known as positional encoding, so that's what we will do first today. And then we'll talk about something known as residual connections and layer normalization, right? Which we have done batch normalization in the previous course. So it sort of builds on that idea, right? So I'll cover these components today. So let's start with positional encoding. And first thing I'll do is I'll try to motivate the need for positional encodings, right? So let's start. So in the case of RNNs, right, when we had these sequence to sequence models, which were where we had h of t as a function of h of t minus 1 as well as the current input, right. In that case, some positional information was already encoded because you are relying on there is a notion of previous, next and so on, right. But now if you look at the transformer architecture, you had these input tokens, right, and what you're doing is for every token you're trying to calculate a new representation which depends on all the other tokens in the input. Is that correct? That's what you are doing, right? You are trying to calculate a new representation for this token by finding the attention weights that it should pay on all the other tokens and then just summing up the attention weighted values. And you are doing this at all the time steps, right? Now, if I interchange these two words, okay, does the new representation that I compute for this, does it change? Yes, no? No? Why do you think no? Right, right. So if I just want to zoom into that explanation a bit, right, let me just, yeah, so let's look at one word at a time, right. So this is the word. Now we remember that from this word we will be computing the query, right, and then we will have the values and the keys from these words. Of course, you also compute the value and the key from this word itself, right? And now the new representation, right? I'll call it Z1. So this was H1, H2, H3, H4, and I'm just looking at the new representation for this word, okay? Z1. How would you compute that? That's a summation over I is equal to 1 to 4 in this case because the sequence length is 4. Q1 transpose Ki, is that okay? Multiplied by Vi, is that okay? Right? So now this is a sum of terms. Now the order in which I add them does not matter, right? So even if these two words were swapped, right, my actual sentence was I am home today, right, and instead of that I am today home, then this would not have changed, right, because whatever representations I am home today, right. Now if I just swap these two words, my final representation would remain the same. Does that make sense? Right. So what is happening here is that the model has no notion of position. It does not know that the word home is farther away from I as opposed to today, right. And now in a small sentence maybe it does not, like, really the idea does not come out, but if you have a very long sentence, right, then it may be the case that words which are farther away are perhaps not so relevant for the current word, right, if you have a very long sentence, right. Or maybe in some cases the word farther away is more relevant than the word nearer. But in either case, you could argue that the notion of distance matters, right. You should know what is the position of these words so that you could know some relative position of the words. You can know that this word is nearer to the next word as compared to the other word, right. But in the transformer architecture, there's no such notion of word so far. We'll see how to add that notion. In the final architecture, we will have some notion of ordering or position. But right now, there is, whatever we have seen, there is no such position. Do you agree with that? Right? And you see there's a problem with that because we need the order in, if you're going to process natural language text, then you cannot just have arbitrary sentence orders, right? So that will be important. Okay. So let me just see if there's anything more that I want to say on this. Yeah. So when I am dealing with individual vectors, right, so now I am talking of this as a column vector, and these are also column vectors, and then it goes through, where the calculation goes through, right. If when you are doing the matrix operation, you just need to make sure that the dimensions are aligned, right. So that whether you are treating it as a column vectors or row vectors, and then it would be V or V transpose accordingly, right. So you just need to focus on the dimensions in the equation, and the dimension of the left hand side should be equal to the dimension of the right hand side. Now I am taking the liberty of just treating both sides as column vectors, so this I don't need a transpose here. Okay, yeah, so just to continue a bit more on this, right. So, and just want to drive home the point that order matters. Now, if let's assume that I am using this for translation, okay. So, I have the encoder. Now, these are the 8 layers of the encoder, okay. I am just drawing it as one black box, right, and the output is the refined representation of these 4 input words, right. Now, since I am going to use this for translation, I am going to pass this to the decoder now, right. So, these will go to the decoder, all 4 of them will go to the decoder, right. Now, if I have not captured the positional information, right, then whether I feed it I am home today or I today home am, it will just have to generate the same translation, right, which is not what you have trained it for, right. You have given it sequences in a particular order, and you want to make sure that the idea of position is captured here. Do you understand that? Right. So that's why we need some notion of position, which is currently missing from the model, okay, which was not the case in RNNs because you are processing it sequentially. So HT was dependent on HT minus 1. So anyways, one word was getting processed at a time. So you knew that by the time you come to the 4th word, your H1 has been modified multiple times. Is that clear, everyone? Okay. So yeah. So this is what it means, right? It's permutation invariant is what I was saying, that even if you permute the input sequence, you'll get the same output, right? So it is necessary to encode the positional information. So how do we include the positional information? That's the question, right? Now, where can you include the positional information? Once again, I'll draw, and you have H1, this is the input that you're given, right? This is H1 up to H4 in this case, and each of these is some 512 dimensional vector, right? And these are word embeddings as we call them, right? So you will initialize the word embedding matrix, and this will be picked up from there. Is this understood by everyone? Yes? Do you understand the concept of word embeddings, right? We've done that previously. Yes? Okay. Right. So this would be we'll have a vocabulary cross 512 matrix, where every row belongs to one word in the vocabulary. Suppose this row belongs to I. So whenever I have I here, I'll pick up that 512 dimensional embedding. Yep. But of course, in practice, we also train this. So this is just a parameter matrix, the embedding matrix, and this will get trained along with all the other parameters, right? But we are picking up some 512 dimensional embedding. And this 512 dimensional embedding does not have the position information. Right? And the position information, it makes sense to provide it at the input when I am feeding it the words. At that time, I should tell it that what is the position of the words. Does that make sense? Right? So now the question is, how do I add the position information here? How do I make sure that the model somehow understands this is 1, this is 2, this is 3, or at least understands that this is farther away from the first word as opposed to the third word, which is relatively nearer to the first word, right? So to somehow add this notion inside the embeddings. So how do we do that? Yeah, so these are our embeddings, the 512 dimensional embeddings, which I said we pick up from the embedding matrix. But now I want to also tell it that what is the position, right? So one way is to have something known as a positional embedding, okay? With whose job, as the name suggests, would be, one option is to have a positional embedding, right? And that we could add to the word embedding. This is the word embedding, okay? Just look at the diagram for now, right? This is the word embedding, and I'm suggesting that let's have a positional embedding. Suppose this is the word I appearing at the first position, right? Then you add a certain embedding to it, which is again 512 dimensional, right? And if the word I appears at position 4, then you add a different positional embedding to it, which is again 5 and 2 dimensional. And we need it to be 5 and 2 dimensional because you're going to add the embeddings, so you can add only same sized vectors, right? Now the question is, what should the positional embedding look like? One option which I want to give you straight away is that if it's at position 0, which is the first position indexing at 0, then just make all of it as 0, right? If it has position 1, just make all of it as 1. If it has position 2, right, so the embedding for position 1 would be just all 1s. The embedding at position 2 would be just all 2s. Is that okay, everyone? This is one option. Okay, do you see a problem with this? Not that generalized. If it's the 256th word, then this would be all 256. You see that? Right? Now the challenge with this is that these numbers are much larger than what you typically initialize your parameters to. Right? And now if you're going to add a very large number to your word embedding, right? So this would all be values like 0.01, say 0.045 and things like that, right? Now if you're going to add the number 256 to this, the original information in the word is going to get drowned and only this will be prevail, right? But of course you could do the same thing. You could say that I'll just multiply all these numbers by 10 raised to minus 3. Then still it maintains some position, and now it also comes in the range of what you have. So what's the problem with that? Yeah. So the problem with not multiplying was that these are very large numbers, your embeddings are small, then the range mismatch happens, right? And just bring it to some small number, but still that it's 0.001, just you're counting from 1 to 256, but in the range of 10 raised to minus 3, right? So what is the problem with that? Yeah, that is the solution I am proposing, right? That you will add something, right? And that something should have position information. Now you are questioning why add, right? That's a separate question, right? But given that we have agreed on adding something, why not do this? Why not just have a constant? So another, as the number increases, right? This is like a linear scale you are increasing, right? And your embeddings are not increasing in that scale, right? So you always hit some problem after a certain sequence length, right? So it does not make sense to have it as a constant number. Okay, fine. So, okay. So then what's the other option? Can you use one-hot encodings, right? So you just again the same thing. You have the sequence length, max sequence length defined as capital T. Maybe that is say 512 or 256 or 1024. So for every position, you just have a one-hot encoding vector. So if it's position 1, encode it as 1 and all zeros. If it's position 2, encode it as 0, 1 and then all zeros, 0, 0, 1 and all. So we understand what one-hot encoding is. So is that okay? Okay, so his point is that we may lose some information. Is there any other way you can argue about this? It will be a very sparse matrix, which generally does not look good. The other option is to just learn the embeddings. Right? So you just initialize embeddings as you initialize any other parameter, right? So this is the embedding for position 0, this is the embedding for position 1. I'm just initializing them randomly, right? And then just as you learn any other parameter, you also learn the positional embeddings. Is that fine? But there's a challenge with that too. So these two questions, why we should not use one-hot embeddings and why there might be a problem with just initializing it randomly, is something that we'll revisit, of course. But this explanation that I'm giving, right, is a bit obsolete in the sense that a lot of advances, like a lot of new types of positional embeddings have come up. What I'm going to explain today is the positional embedding in the original transformer architecture, right? But today there are other positional embeddings which are more relative in nature, and we will cover that at a later point in the course. And we'll also look at arguments where people say that, hey, you don't even need positional embeddings at all, right? So this, whatever I'm doing now is as if I'm sitting like 3 years back and trying to explain why positional embeddings are required. But later on in the course, I'll also argue the other way around and look at some recent work which says that, hey, maybe you don't need positional embeddings at all, right? Although it's not still an evolving argument, right? It's not clear that that argument has won, but there is also an alternative view, right? So just take it with that pinch of salt, right? Okay. Yeah. So none of these actually, right, are suitable if the sentence length is going to be dynamic, right? So you may fix, for example, the max sequence length to be 5 and 12, right? Now in your training data, if all the examples that you had seen, suppose you are training for the task of translation, right, and all the sentences that you had seen during training data, say the maximum length was 40 words, okay? So you have trained the positional embeddings from 0 up to 40 or 1 up to 40, right? Now at test time you get a new sentence which is of length 44, right? Now for the words 41, 42, 43, 44, you have never trained this positional embedding before, right? So if you go for this option, then you have a problem now, right? Because you have never learned those embeddings, right? You initialize those embeddings. Maybe you initialized all the 5 and 2 embeddings, which was your max sequence length. But during training time, if you did not see any sentence which was greater than a certain length, then you'll have a problem. Or if you saw the sentences of length 30, 35 only a few times, which is possible because it's a very large length, then those embeddings will get trained fewer times. Does that make sense? Right? That's why learning the embeddings may not be reasonable. So you'll need probably some other option. Learning the embeddings from scratch. You may initialize it to something reasonable and then try to learn, maybe that will work, and that's what we'll see eventually. But just learning, initializing the embeddings randomly may not work, right? The other argument for not initializing the embeddings randomly, maybe I'll come back to that later, right? And that argument also holds for why you should not do one hot embedding, right? So what we have done so far is say that, hey, the original word embeddings don't contain any positional information. If the word I appears as the first word or it appears as the 10th word, I have the same input going through the transformer, right? I want to change that. I want to say that I first, I 10th, right? And the proposal is that take the embedding of I, add another 5 and 2 dimensional vector to that, and that 5 and 2 dimensional vector contains the position information, right? And we discussed a few bad options. One bad option was to say that the positional embedding is just a constant number 1, 2, 5 and 2, right? The other bad option was to have one hot embeddings, which you said would be very sparse. There is one more problem with one hot embeddings, which I'll come to later. The other option was to have randomly initialized embeddings, which we learn from scratch during training, just as we learn any other parameters. But there, this problem of sparse learning can again happen if for whatever reasons you never encounter a sequence of length 30, right? Exact number 30, right? Then that embedding will never get initialized, right? Position 30, and in the test time, if you see sequences which are of greater length than what you have seen during training time, then those embeddings have not been learned at all, right? They're all still with their random initialization, right? So this is one set of problems. There is one more problem which I have not said yet, and I'll come back to that later. Okay, so let's see then what else can we do. Okay, maybe I should say that problem first, right? So if you use one hot embeddings, okay, what's the distance between the embedding of the first word, the positional embedding? I'm asking about the distance only between this guy, not this plus this or not this. I'm just asking, suppose you have the first word and the second word, right? And you're using one hot embeddings. What would the distance between these two be? So this is 1 and then all zeros. This is 0, 1 and then all zeros. So what is the Euclidean distance between them? Square root of 2. Everyone agrees with that? Okay. Now 3. So 0, 0, 1 and then all zeros. What's the difference between position embedding of 1 and 3? Square root of 2, right? And you see that up till 5 and 2 this argument will remain the same. For any two positions, the distance will remain the same. Does this capture the idea of position? It does not capture the idea of relative distance, right? You would ideally want that the distance between the positional embedding of the second word and the 10th word would be greater than the distance between the positional embedding of the second and the third word. That does not happen in this case. Do you see that? It may not also happen in this case because you are randomly initializing it. So if you are randomly initializing it, you have no control on the distances, right? So if you have randomly initialized all the word embeddings, then it's possible that 5 and 2 and 5 and 1 are farther away from each other as opposed to 5 and 2 and 25, because it's a random initialization after all, right? So that's the other problem that you have. This position of relative distance is not encoded if you look at one-hot encoding or random initializations, right? Of course, you could argue that if you do random initialization, over a period of time it may learn it, but then that's a harder problem that you're putting on the embeddings to learn. You're putting more sort of overloading the embeddings to learn that, right? Can you just come up with a method that's already encoded in the embedding, where nearby positions have a smaller distance and farther away positions have a larger distance? Okay, so that's what we will head towards.